This is a video from section 4.4 in a linear algebra class. Explain why the following form linearly dependent sets of vectors. 1a. Suppose we're given the vector u1, which is negative 1, 2, 4, and vector u2 is 5, negative 10, negative 20 in R3. If I take the vector 5, negative 10, negative 20, we can write that as negative 5 times the vector negative 1, 2, 4. So u2 is equal to negative 5u1. And so notice, u2 is a scalar multiple of u1. And so therefore the set containing vectors u1 and u2 form a linearly dependent set. 1b. Suppose we're given the vectors u1, which is 3, negative 1, u2, which is 4, 5, and u3, which is negative 4, 7 in R2. If I take negative 2 times the vector 3, negative 1, and add it to 1 times the vector 4, 5, I get the vector negative 4, 7. And so negative 2 times u1 plus 1u2 equals u3. And so u3 can be written as a linear combination of vectors u1 and u2. And so therefore, the set containing the vectors u1, u2, and u3 form a linearly dependent set. And that's how you do problem number 1b. Let's take a look at 1c. Suppose P1 is equal to 3 minus 2x plus x squared, and P2 is equal to 6 minus 4x plus 2x squared in P2. And remember, P2 is the set of all polynomials of degree less than or equal to 2. So if I take 2 times 3 minus 2x plus x squared, I get 6 minus 4x plus 2x squared. So I'm just applying the distributive property here. And so therefore, 2 times the vector P1 is equal to the vector P2. And so P2 can be written as a scalar multiple of P1. I'm done. So the set containing vectors P1 and P2 form a linearly dependent set. 1d. Suppose we're given A is the matrix negative 3, 4, 2, 0, and B is the matrix 3, negative 4, negative 2, 0 in M22, which is the set of all 2 by 2 matrices. If I take negative 1 times the matrix negative 3, 4, 2, 0, I get the matrix 3, negative 4, negative 2, 0. So therefore, negative 1a equals b, right? And so b can be written as a scalar multiple of a. And so the set containing matrices a and b form a linearly dependent set. That's 1d. 5a. Now, suppose we're given this set of matrices. So the first matrix is 1, 0, 1, 2. The second matrix is 1, 2, 2, 1. And the third matrix is 0, 1, 2, 1 in the set of all 2 by 2 matrices. So in other words, in M22. Is this set linearly independent or linearly dependent? So I'm going to take C1 times the matrix 1, 0, 1, 2 plus C2 times the matrix 1, 2, 2, 1 plus C3 times the matrix 0, 1, 2, 1 and set it equal to the 0 matrix. So when I unwind this and set up my system, I get the following. I get C1 plus C2 equals 0, 2C2 plus C3 equals 0. And then I get C1 plus 2C2 plus 2C3 equals 0. And then I get 2C1 plus C2 plus C3 equals 0. Now notice, if I solve for C1 in terms of C2, I get C1 equals negative C2 right here. And then if I solve for C3 in terms of C2, I get C3 equals negative 2C2. So I can plug into the fourth equation here, or the third equation. And I claim you're going to find that C2 equals 0, regardless of where you plug things in. So in other words, if you look here, I replace C1 with negative C2, and I replace C3 with negative C2 times 2. So I plug into the fourth equation. When I plug into the fourth equation, notice that I get C2 equals 0. And if C2 equals 0, you're going to quickly see that C1 equals C3 equals 0. And this set will be linearly independent. Or, if you come over here, I plugged into the third equation, and I got that C2 equals 0, and therefore C1 and C3 are 0. Either way it goes, the set containing the matrices 1, 0, 1, 2, 1, 2, 2, 1, and the matrix 0, 1, 2, 1, this is a linearly independent set. 5b. Suppose I'm given the set of matrices 1, 0, 0, 0, 0, 0, and then 0, 0, 1, 0, 0, 0, and then 0, 0, 0, 0, 1, 0 in M23, which is the set of all 2 by 3 matrices. Is this set linearly independent or dependent? So I'm going to take A times the first matrix plus B times the second matrix plus C times the third matrix and set it equal to the 0 matrix. A, B, and C have no choice but to be 0. There's no choice. And so therefore, the set containing the matrices 1, 0, 0, 0, 0, 0, and then 0, 0, 1, 0, 0, 0, and 0, 0, 0, 0, 1, 0 is a linearly independent set. And that's how you do 5. In number 6, determine the values of K for which the following matrices are linearly independent in the set of all 2 by 2 matrices. That's what M22 represents. So the matrices are 1, 0, 1K, negative 1, 0, K1, and then 2, 0, 1, 3. So I'm going to take C1 times the first matrix plus C2 times the second matrix plus C3 times the third matrix and set it equal to 0, 0, 0, 0. Now, when I set up my system, notice how I get C1 minus C2 plus 2C3 equals 0, C1 plus KC2 plus C3 equals 0, and then KC1 plus C2 plus 3C3 equals 0. This is a great question, because remember we get an associated matrix equation from this. So we could write this as 1, negative 1, 2, 1, K1, K1, 3, times the column vector C1, C2, C3. And this is equal to the column vector 0, 0, 0. Now, if this coefficient matrix is invertible, then the column vector C1, C2, C3 has to equal the 0, the column vector comprised of all zeros. In other words, it's going to force C1, C2, and C3 to all be 0, because the only solution to that matrix equation is the trivial solution by the equivalence theorem. Let me say that again. If A is invertible, the only solution to this system is the trivial solution. And that means that C1, C2, and C3 are all 0. And so I restated my matrix equation, and what I did was I let A equal the matrix 1, -1, 1k1, k1, 3. By the equivalence theorem, if A is invertible, the only solution to the system is the trivial solution. So we need to figure out what's happening here. So we want the values of k that make A invertible. And remember, and this is a big theorem, I can't stress this importance. A is invertible if and only if the determinant of A is not 0. And so what I want to do is I want to find the values of k that make A not invertible. Because if I know the values of k that make A not invertible, that means A is invertible for all the other values. And so I'm going to set the determinant of A equal to 0. When I do that, this is what my equation looks like. So I expanded around the first row. And when I did that, I ended up with k squared minus k minus 2 equals 0. When I solve for k, I get k equal to 2 or k equal to, that should say -1, by the way. So when I solve for k, I get k equal to 2 or k equal to -1. Okay? And do you guys notice to go from here to here, I divide everything by -2. And then come over here. A is not invertible when k is 2 or k is -1. And so A is invertible for all real numbers except 2 and -1. Right? It's going to be invertible for all other values of k. And so therefore, the set containing the matrices 1, 0, 1k, -1, 0, k1, and 2, 0, 1, 3 form a linearly independent set for all k except 2 and -1. And that will do it for this video for section 4.4. And in this video, we looked at problems 1, 5, and 6. Thank you.